Okay, we are continuing with the further maths chapter summaries, and this is chapter 8, proof by induction. And as I always say in these videos, it is not possible for these chapter summaries to cover all of the ways that it can be assessed. So please do make sure that you're looking at lots of exam questions for this. So the only kind of thing I'm really going to mention here is sort of what proof by induction actually looks like, the different steps. We have the first step, which is the basis step, where you prove that it's true for the base case for n equals 1. You then write down your assumption that it's true for n equals k. This is the bit where all the maths happens. You need to then do the inductive step, where we assume from the assumption we need to show that it's true for n equals k plus 1. And then at the end we have a conclusion. A tip that I usually have is for the series questions and the matrices questions, write down what you are aiming for in the inductive step. It usually makes that last part with the algebra a little bit easier. And I'm going to be looking at a series one, a matrix one, and a divisibility proof. There is a very, very small chance they could do something to do with recurrence relations. Edexcel have done a question on that in a further maths mock set question. And they do also talk about the nth derivatives, but this uses year 2 differentiation. And it's not kind of technically covered in this chapter. So I've left it out of this chapter summary so that it's really focused on stuff with year 1. Okay, we're going to begin by having a look at a series proof question. And it says, prove by induction that for any positive integer, this thing is always equal to n squared n plus 1. Now, it's important they've said by induction. If they didn't say by induction, we could have used sort of chapter 3 techniques for this, but we're going to obviously use induction for this. So the first thing is we need to show that it's true for n equals 1. So show that it's true for n equals 1. Now, the left-hand side of the equation, we would have the sum from r equals 1 to 1 of r, 3r minus 1. In other words, we just substitute 1 into that. So that's 1, 3 minus 1, which is just 2. Now, for the right-hand side of the equation, we are going to substitute n equals 1 into n squared n plus 1. So that's 1 squared times by 1 plus 1. That is also equal to 2. So because they're both equal to 2, we can say, hence, it is true for n equals 1. Hence, it is true for n equals 1. Now, we'll do the assumption step. We are going to assume that this is true for n equals k. In other words, that thing that we've got at the top, the sum from r equals 1 to k of r 3r minus 1 is equal to k squared k plus 1. Now what we're going to try and do is the inductive step. We're going to show that it's true for n equals k plus 1. Show true for n equals k plus 1. And this is where I really want to say, what is the thing that I am aiming for in this question? Because it's for k plus 1 for n, well, instead of there being an n squared, there would be a k plus 1 squared. And instead of there being an n plus 1, it would be a k plus 1 plus 1, or a k plus 2. So this is the thing that we're going to be aiming for in the question. So we are trying to do the sum from r equals 1 to k plus 1 of r 3r minus 1. Well, let's do that into two things we know. I already know the sum from r equals 1 to k of r 3r minus 1, because that's the thing we have literally just assumed down here. So I already know exactly what that thing is going to be. And because we're actually now going up to k plus 1, I just need to add on what it would be when you substitute k plus 1 into the rth term formula that we've got there. So that would be adding on a k plus 1, and then for the next part, 3 lots of k plus 1 minus 1 like this. Now, I did say this just here. This thing is the part that we've assumed down here, okay? So I can say that that is k squared k plus 1, k squared k plus 1. And then for the next part, we have a k plus 1. And then for the next bracket, there is a 3k plus 3. So it's a 3k plus 3 minus 1. So it's a 3k plus 2. Now, given the thing that I'm aiming for has got this k plus 1 as a factor, and there's a k plus 1 and a k plus 1 here, much like chapter 3 series, we're not going to expand everything. We're actually just going to factorize out a k plus 1 to begin with. It should make the maths a lot neater. So I'll do a k plus 1. Now, from taking k plus 1 out of the first part, that leaves us with a k squared. And for the second part, that leaves us with a 3k and a plus 2 like this. Obviously, you could have it with brackets, but it's not going to make much of a difference at the end. And actually, I think this is pretty much what we're going to be looking for. It looks like that second bracket that we've got is a quadratic. I think it should factorize to a k plus 1, k plus 2 to give us the thing that we are aiming for. So that's a k plus 1. Does it factorize like that? Yeah, I think it does. A k plus 1, k plus 2, yeah, it does factorize, which means that we have it as a k plus 1 squared and a k plus 2. If you wanted to be really fussy and make it look exactly like it was in this form here, we could write it as k plus 1 squared and then k plus 1 plus 1 to show that it's sort of got the exact same structure where there's just that part squared and there's that extra plus 1. However, this line here I don't believe is necessary. So we've done those three things. We've done the basis, the assumption, the inductive step. And then to save time for the conclusion, I've actually pre-written the conclusion. But you can check that you've got something similar to what I've got here, just because I didn't want you to sort of sit here and watch me writing long sentences out. So we say something like this: hence, as it was true for n equals 1 and was true for n equals k plus 1 when it was assumed true for n equals k, then the statement is true for any positive integer n. And I've copied that kind of language that they've used in the question there. So we're going to do the same thing for matrix proof, but I've got it all written here. I don't even need these steps. It's the same as before, so I've kept this page kind of nice and clean for this. So we have a matrix A103, where A is a constant, proved by mathematical induction that for n as a natural number, this means that n is a member of the natural numbers. In other words, it's just the positive integers. Sometimes people include 0, sometimes they don't. But we are going to go with this. So we're going to do m to the power of n is equal to this thing. So let's start off by doing the basis step. Let's show that it's true for n equals 1. So the left-hand side is just m to the power of 1, which is m, which is A103. The right-hand side is going to be our a to the n, 3 to the n minus a to the n over 3 minus a, and then 0 and 3 to the n. So if I substitute in n equals 1, we get a, 3 minus a over 3 minus a, 0 and 3. And actually we can see that's going to be the same thing, right? Because obviously this is a, 0 and 3. Numerator is the same as the denominator, so it is a 1. So we can just say hence true for n equals 1. Now we will do the assumption step. Let's assume that it's true for n equals k. In other words, m to the power of k is going to be equal to a to the power of k, 3 to the power of k minus a to the power of k over 3 minus a, 0 and 3 to the power of k. Now we'll do the inductive step. So again, I like to say the thing that we are aiming for. Let's say what we are aiming for in this question. It is going to be an a to the power of k plus 1, a 0 and a 3 to the power of k plus 1. There'll be a 3 to the power of k plus 1 minus a to the power of k plus 1 over 3 minus a. It's that element in the top right that I'm not looking forward to, but I think we should be able to do it. It looks kind of like a messy one, doesn't it? So now let's show that it's true for n equals k plus 1. In other words, we're trying to do m to the power of k plus 1. Well, m to the power of k plus 1 is m to the power of k multiplied by m. Or we could think of it as the other way around, m multiplied by m to the power of k. Remember, you're just sort of like, you can add the powers together like this. So m to the power of 1 we already know. So I'm just going to do the m, which is my a, 1, 0, 3, and I'm going to multiply that by my m to the power of k, which is the one that I've got down there. So that's my a to the power of k, 0, my 3 to the power of k, and then my more complicated one, 3 to the k minus a to the k over 3 minus a. Gosh, that doesn't look very neat, but we'll have to just say that's okay, that's good enough. So now we'll do some matrix multiplication, okay? We are going to do this times this. Well, that's just an a times by a to the power of k. A times a to the power of k. And then the complicated one is coming up. We're going to do these times these. So it's a multiplied by this. So this is a multiplied by 3 to the power of k minus a to the power of k over 3 minus a, plus this one times this, which is 3 to the power of k. And then the other ones should be a bit easier, right? We're going to have this times this. That's just a 0 and a 0. Good. And then this times this. Well, that's a 0 and this, and just a 3 times 3 to the power of k. So that is just a 3 times 3 to the power of k. Now, the messy one is the top right, okay? I think pretty quickly we're going to be able to see what these things here are equal to. This is just a power of 1 and a power of 1, so we do get an a to the power of k plus 1. we do get an a to the power of k plus 1 and a 0 and a 3 to the power of k plus 1. This thing right here is the thing I want to work on. So I could actually do that somewhere else on the page. That might be a nicer way of kind of working out what's going on and not having to keep writing the whole matrix out again and again. So I'm going to try and think about what I want this whole section here to resemble. The thing that we're aiming for, it has a common denominator of 3 minus a. So I think I'm going to try and make it have a common denominator of 3 minus a. So we have a multiplied by 3 to the power of k minus a to the power of k over 3 minus a. If I give it a common denominator, the 3 to the power of k must also be multiplied by a 3 minus a so that it looks like this, right? So now that I've got it here, not the highlighter, I'm going to use the eraser so I can just put that plus sign exactly where I want it. Now I can just keep working on this. So I have a multiplied by 3 to the power of k minus a times by a to the power of k plus 3 times 3 to the power of k minus a times 3 to the power of k, all divided by 3 minus a. Now, do you notice anything in the numerator? This and this cancels out, which then just leaves me in the numerator with this. That's like a 3 to the power of 1. This is like an a to the power of 1. Great. This means that the numerator is 3 to the power of k plus 1 minus a to the power of k plus 1. I've simply just swapped these. So I've got the positive one and then the negative one like this. And that is all divided by 3 minus a, which is exactly the thing that we were aiming for up here. This and this are the same as each other. And it's perfectly fine to communicate with the examiner by doing some extra working on this thing somewhere else, okay? So we then get that this is equal to 3 to the power of k plus 1 minus a to the power of k plus 1 over 3 minus a, which is the thing that we were trying to show that it was equal to. So we then save a bit of time here. Hence, as it was true for n equals 1 and it was true for n equals k plus 1 when it was assumed true for n equals k, then the statement is true for n as a natural number. Notice how I've used the same language that is in the question there. Okay? So, this idea of writing it to the side can keep things a bit neater. Otherwise, I would have had to keep writing this matrix out lots and lots of times here. We're going to finish off with the divisibility proof, and divisibility proofs are, I think, one of the trickiest. I think they probably, for me, I think they can be one of the more challenging questions because there's lots of different things they can ask for. So do make sure that you're really, really prepared for the divisibility type of questions. Now, there are many possible approaches to these, but my personal preferred method for the inductive step is to use this. If you don't use this, if you've never been taught this, then just keep doing what you do. You should still end up with the same conclusions that I do. However, this is the way that I like to do this in my videos and my teaching. So you'll see me using this inductive step when I go through this, okay? So I'm going to prove for n as a member of the positive integers. This means positive integers. We're going to prove that this thing is divisible by 5 that we've got here. Now, it can be quite useful to start off by saying something like, let's let f of n be equal to 2 to the power of 2n minus 1 plus 3 to the power of 2n minus 1. It just means we can then use this function notation throughout the question. So let's start off, as we always do, with the base case. Let's show that it's true for n equals 1. So f of 1 will be 2 to the power of 2 times 1 minus 1 plus 3 to the power of 2 times 1 minus 1. So what's that? 2 to the power of 2 times 1. 2 minus 1 is 2. And the same thing for this. This is going to be 3 to the power of 1, so it's just 2 plus 3. Sometimes just the easiest maths is the thing that can trip us up. So we get 2 plus 2, which is equal to 5, which is divisible by 5. Which is, I'm going to use the word clearly. I'm going to say, well, this is clearly divisible by 5. It's so obvious. Okay, we are now going to assume that it's true for n equals k. This means that f of k is f of k, which is equal to 2 to the power of 2k minus 1 plus 3 to the power of 2k minus 1 is divisible by 5. That's all we have to write. We just have to say, we're assuming this thing is divisible by 5, okay? I am now going to do the show that. This one doesn't need an aim, okay? We are going to show that this is true for n equals k plus 1. You know how we did the red aim part here and here? This one doesn't have an aim. It doesn't have something we're aiming for. So we're now going to do f of k plus 1. My trick is to do f of k plus 1 minus f of k. So I'm going to substitute k plus 1 into this. That's going to be 2 to the power of 2 lots of k plus 1 minus 1, plus 3 to the power of 2 lots of k plus 1 minus 1, and then I'll subtract f of k. So I'm going to subtract this thing here. I'll subtract this, and I'll subtract this. That's minus 2 to the power of 2k minus 1, minus 3 to the power of 2k minus 1. So for the power here, 2k plus 2 minus 1 is just going to be 2 to the power of 2k plus 1. And then I'm going to take this thing and put it right next to it. So it's minus 2 to the power of 2k minus 1. The same thing for the 3. It's going to be 3 to the power of 2k plus 1 minus 3 to the power of 2k minus 1. And at this stage, what we want to do is make these new powers that we have here look like these old powers. And 2k plus 1 is 2 greater than 2k minus 1. So I can actually rewrite this as 2 to the power of 2 times by 2 to the power of 2k minus 1. Just think what happens with the powers there. 2k minus 1 plus 2 gives 2k plus 1. And then we still have this one. Same thing for the 3. We're going to have a 3 squared times 3 to the power of 2k minus 1 minus 3 2 to the power of k minus 1. Now, there's lots of different ways of thinking about this. Probably the easiest way to see this is that you can see we have a common factor of 2 to the power of 2k minus 1. So if I do 2 to the power of 2k minus 1, we then have a 2 squared minus 1. And here we have a common factor of 3 to the power of 2k minus 1. We then have a 3 squared and a minus 1. In other words, we now have 2 squared minus 1, that is 3 lots of 2 to the power of 2k minus 1. And we have 3 squared minus 1, that's 9 minus 1, which is 8. We have 8 lots of 3 to the power of 2k minus 1. Now, in an ideal world, because we're trying to show that something is divisible by 5 in this question, we would then go, oh, great, we've got this is a 5 and this is a 10 or a 15, but unfortunately we've got 3 and 8 here, and neither of those are divisible by 5. However, when I see the number 3 and I see the number 8, there is a 5-ness there. There's an inherent 5-ness because 8 take away 3 is 5. So in this question, we can use a particular trick. We can split this 8 up into a 3 and a 5. So I have 8 lots of this means I can say that it's 3 lots of this plus 5 lots of this. Okay, this is what f of k plus 1 minus f of k is equal to. And I know I'm going to need some more space, so I'm going to jump up here for this next stage of this, okay? Now, this thing that we've got written here and here, we have 2 to the power of 2k minus 1, 3 to the power of 2k minus 1. It is the same as f of k, and they've been multiplied by 3. If I really needed to, I could factorize out the 3, and you can clearly see that this thing is 3 lots of f of k. So we now have that f of k plus 1 minus f of k is 3 lots of k, 3 lots of f of k, excuse me, plus that last term, which is 5 times by 3 to the power of 2k minus 1. I'm going to need to give myself just a little bit more space, I think, for this question. So let's just take this and just pull this along a bit here, like this, okay? And I'll sort out that mess that I've made in just a second, okay? So, last thing that we need to do is just to do a bit of a conclusion statement, because if I now add that f of k to the right hand side, we have 4 lots of f of k plus 5 times by 3 to the power of 2k minus 1. Now we can clearly see as f of k is divisible by 5, so is 4f of k. 5 times 3 to the power of 2k minus 1 is also divisible by 5. Hence, f of k plus 1 is divisible by 5. If this thing is a multiple of 5 and this thing is a multiple of 5, when you add two multiples of 5 together, this thing is still a multiple of 5. Hence, as it was true for n equals 1, and it was true for n equals k plus 1, and when it was assumed true for n equals k, then the statement is true for n as the positive integers. Now, these divisibility questions, they don't always have this idea of needing to split something up. You may have had like a 5 here and a 15 here that is immediately divisible by 5. I deliberately picked this question because it had a little bit of an extra twist to it, where we had to do some kind of splitting up of this. I think definitely divisibility proofs are the most challenging ones that we have for this. So that's everything for proof by induction. Do make sure that you look out for potential other ways they could ask it in the real exam as well. But I hope this has really refreshed your memory on this topic. If you are interested in applying for a Bison Maths scholarship, this is something that I run every year. So go and check out and see if the Bison Maths Award is currently running whilst you're watching this video. Just search for it on YouTube, and it might be something that's currently open. It is currently open at the time of this video being uploaded in October 2025. Wishing you the best of luck in your studies, guys, and I hope to see you in another video sometime soon.